In this video, we're going to talk about how to calculate partial derivatives. In the last section and the last video, we saw that partial derivatives, like single variable calculus derivatives, are defined using limits. But if we had to use a limit every time to calculate a partial derivative, that would be really cumbersome. Luckily, we can apply the derivative rules from Calculus 1 to find partial derivatives. To see why this is true, we're going to let f of xy be a function, and we're going to let y be held fixed. So if y is a constant, then f of xy becomes a function of a single variable, x. If y is not changing, x is the only variable. So we can let g of x be the function of f of x and some constant value y. Then g prime of x, well, it's defined, you'll remember, as the limit as h goes to 0 of g of x plus h minus g of x over h. But g of x is f of x with some constant y. So that means that this is the limit as h goes to 0 of f of x plus h with our constant y minus f of xy over h. But that is exactly the definition of the partial derivative of f with respect to x. Therefore, to find del f del x, we need only pretend that y is constant and apply the derivative rules to a function of a single variable as if we were finding g prime of x. A similar argument tells us that we can do the same thing for del f del y, except of course we'll hold x constant and apply the derivative rules as if we had a function of y. In fact, the same principle applies no matter how many variables our input function has. So how many input variables our function has. So let f be a function of n variables. To calculate del f del xi, the partial derivative with respect to the ith variable, which can also be written of f sub xi of x1 through xn, we will hold all variable constant except xi. And we'll apply the normal derivative rules to f as if it were a function of a single variable xi. So let's do example 3.3.1, where we'll put this into practice. This example is asking us to calculate all the first order partial derivatives for the following function. So part A, f of xy is the tan of x squared y. So if we want to calculate del f del x, then we are going to pretend that y is a constant. For example, y could be 2, y could be 7. You can imagine that y is just some constant value. So we have to apply the first calculus 1 derivative rules. And so the derivative of the tangent is the secant squared. We'll hold the inside function the same, and now we need chain rule. We have to take the derivative with respect to x, which is going to give us 2x, and y is a constant, so we'll just tag it along. If we want del f del y, well, we're going to do the same thing, but now we're going to pretend that x is a constant. Therefore, x squared is a constant. Any expression involving x will be just a constant. We have an outside function, it's the tangent, so the derivative is still the secant squared, keep the same inside function. But now we're taking the derivative with respect to y, so we're pretending the variable is y, that's going to leave us as x squared. B, we have g of xy is x to the y. So let's switch notations here to practice getting used to both. If we want g sub x of xy, we are going to hold y as a constant. That's like we had x to the 2, x to the 3, x to whatever number we have, which means that the rule we're going to apply is the power rule. So we have y x to the y minus 1. Next, if we want g sub y, the derivative, the partial derivative with respect to y, then we are going to reverse the rule. So x is now the variable and y is held constant, which means, oops, nope, that's the opposite. Y is now the variable and x is now constant. The hardest part about taking these derivatives is to remember what is constant and what is the variable. So we are imagining that we have something of the form like a to the x, except we don't have x as our variable, we have y. And we're thinking that x is equal to a is our constant value. And if you remember from your calculus, a derivative of a function of that form Well, the derivative of a to the y was a to the y times ln a. And so that is exactly what we have here, except we've got x to the y times ln x. Part C is a function of 3 variables, but the exact same principles apply, except we're going to take turns in which of the variables we hold constant. So if we want del h del x, that we're going to hold y and z constant, which means that x is our variable. Now we see we have 2 x's there with a multiplication in between, so we need a product rule. So the derivative of the first is 1 times the second function of x plus the first times the derivative, and this is again a function of this form, an exponential. So we're going to have z to the x, y, z times ln z, but now we have an inside function as well. We have to take the derivative with respect to x, y, and z are constants, so we have times yz. Del h del y. So now y is our only variable, so x is a multiplier in front, like 12, like -4, whatever. X is just a constant multiple, so x is going to hang along for the ride, times z to the x, y, z times ln z, and now we have the derivative of the inside function. Y is the variable, so the x and z are constant, so we get times xz. And lastly, del h del z. X is again a constant multiplier, so we'll say x here. And now we have a little bit more of a complicated situation. We have z down in the base and z up in the exponent. So we might actually take the opportunity to rewrite this using our inverse function rules, that we can write this as e to the ln of z x to the ln e, this is hard to say, e to the ln of z to the xyz. There you go. This, of course, using the laws of logarithms, we can take this and bring this down in front of the logarithm, so that becomes x times e to the xyz times ln z. So back to our rule here, x is a constant multiplier out in the front, which means we need to take the derivative of this part now with respect to z. So we have an exponential function, first of all. So the derivative of the exponential function is the same exponential function times the derivative of what's inside. And what's the derivative of what is inside? We see we have z in 2 places. We're going to have a product rule. So derivative of the first is going to be, well, x and y are constants. So x and y times the derivative of z, which is 1 times the second, ln z. Plus, lastly, we've got, again, x and y as constants. The first times the derivative of the second. We can do a little bit of cleanup here with this. Our e to the xyz ln z, that was the original z to the xyz that we had, so we can rewrite that as x z to the xyz times xy. In fact, why don't I factor out an xy? So we're going to get x squared y times, and we'll be left with ln z plus 1 in the brackets. As I was saying before, the hardest part of this is concentrating and remembering which variable is constant, which variable is actually the variable of differentiation. Little practice, and I'm sure you will get used to doing that. In the next video, we are going to look at another differentiation technique that you might remember from your first course in calculus, and that is implicit differentiation.